So in today's class, we are going to show you how abstract algebra plays an important role in our real life. So basically how number theory and abstract algebra, how they are closely related, and many of the proofs of number theoretic proofs can also be done very easily by using this abstract algebra, mostly using the concepts of group, ring, and field. So still we do have only groups, not even ring or field, but still I will try to show you a few of the results which could be proved by using these concepts. Okay, so let us first have a look at a few historical aspects of number theory. So most importantly or most interesting numbers among our real life is basically the prime numbers. So prime numbers are very important and they are very interesting as well. Uh, if you look at the very old history of prime numbers, then you see that the ancient Greek people, so they had the idea of prime numbers. So Pythagoras school, so you might have heard about the name Pythagoras. Think about it, they are more than 2,500 years old. The mathematician of Pythagoras school were interested in numbers for their mythological as well as numerical properties. Okay, so we all know about Euclid. So Euclid was around 300 BC, so more than 2,300 years back. So he has given a nice proof, and he for the first time shown that there exist infinitely many primes. Can you believe that? Around more than 2,300 years back, somebody is giving the proof of there exist infinitely many primes, and that too by using the concept of contradiction method. So it is assumed that Euclid was the first guy in the history of mathematics who actually used this concept of contradiction method. So he also gave the fundamental theorem of arithmetic, which says that every integer which has to be greater than 2 or greater than equal to 2 can be written as a product of primes in an essentially unique way. So you all know that every integer can be written which is greater than equal to 2 as a product of primes in some specific manner, and that manner is basically the unique way. For example, if you consider 6, then 6 can be written as 2 into 3, or you can say 3 into 2, but both of them, the representations are the same up to the permutation of the primes. So in that way, both of them are very important. So Euclid did a lot of things on prime numbers, but he was, I mean, it's historically not proven that he could give some algorithm to find whether a number is prime or not. So he had given the existence of primes, but it was for the first time Eratosthenes around 200 BC who actually first gave the idea of sieve of Eratosthenes. So you all know what is that meaning of that. So try with all numbers which are greater than equal to 2. So start with first 2, because 1 divides all the numbers. Suppose I want to find all the prime numbers between 1 and say maybe 84, then start with 1, because 1 divides all the numbers, so don't take 1. Then start with 2 and just cross all the numbers which are divisible by 2. So 4 is divisible by 2, then 6 is divisible by 2, 8. So all even numbers are gone. Then take 3 and consider all the numbers which are not previously blocked, like 4, 6, 8, they are already blocked. So consider 3 and start finding all the numbers which are multiple of 3. For example, 3, then start with 6. So 6 is already blocked, so you just make it again blocked. Then 9. So 9 was not previously blocked, now 9 is gone, and so on, 12 and so on. Then start with, so 4 was already gone due to 2. So start with 5. Then all multiples of 5. So 10 is gone, 15 is gone, and so on. So if you continue all the numbers from 2 to 84, whatever will be the left, that will be the primes. For example, you see that 2, 3, 5, 7, 11, 13, they are not exhausted by any of this multiples crossing method. So that is known as Sieve's method, and that was done, you can understand it, that was done around 200 BC, so long back. So he did it. But after that, there was a long gap in the history of mostly number theory, and that gap is known as dark ages. Okay, after that, it was like a dawn who actually came in the field of mathematics. He was Fermat. So around 1601 to 1665. So Fermat was not actually formally a mathematician. He was a lawyer, and you can Google it. So it's excellent history. You can find it around or about him. So he used to embarrass the a big mathematician at that time. So he has a very peculiar, uh, mind or nature. What he did is basically when he solved some problem, he challenged others. For example, suppose some big mathematicians are there during that age. So he solved some problem and he sent some letter to that big mathematician saying that I solved it. Will you be able to solve this? And then he makes it public that okay, he couldn't solve this, but I could solve it, and so on. So he was basically a lawyer, but he has again a very peculiar but a very brilliant mind of mathematics, and he did lots of important results of mathematics. So one of the results is known as Fermat's little theorem, but most important result that he did was known as Fermat's last theorem. I will come it to after a few minutes. After Fermat, two big guys who actually worked in the field of this number theory is Euler and Mersenne. So you might have heard about Mersenne prime and so on. Similarly, there are many results done by Euler. In today's talk, I will also talk about few results which are done by Euler. Then let's come to the Fermat's last theorem. So as usual, I told you that Fermat was a very peculiar guy. So you might have heard about this Fermat's last theorem. So it was stated around 1637, but in a different way, not very formally it was revealed. What happened? Once Euler was actually studying a uh, book copy of Arithmetica. The name of the book was Copy of Arithmetica, an ancient Greek textbook written by Diophantus in 3rd century AD. So it was a quite historical book, and Fermat was trying to read this book. So while he was reading this book, the question that came to his mind was like this. So he stated that, okay, if you consider a to the power n plus b to the power n equal to c to the power n, then there is no three positive integer solution for n greater than 2. That means you cannot find all ABC, which are integers, are not all ABC should be non-zero. There exists no non-zero. That's why there's three positive integer solutions for this n greater than equal to 2. So you all know that in case of n equal to 2 or n equal to 1, you will certainly have some solutions. For example, for say a, b, c equal to c, for example, if you consider n to be 1, and if you put a to be 2, b to be 3, then c to be 5. And you can see that there exists infinitely many such solutions. On the other hand, if you consider n equal to 2, then also you'll find that by using the triangle law, you can find that there are plenty of such. Can anybody tell me one of such example which could be useful?
3, 4,
Anybody?
5.
3, 4, 5. Anything else? 3, 4, 5 is the correct answer. Any other
5,
pair, or
12,
is this a
13.
unique one? Anything?
5, 12, 13.
5, 12, 13. Okay. Anything else? Very good.
So 6, 8, 10.
6, 8, 10. How do you prove that? 6, 8, 10. Okay, somebody says it's 6, 8, 10. Let's see.
So 6 square plus 8 square equals to 100 is equal to 10 square.
So 6 square plus
Square.
8 square equal to 10 square. Very good. And you started with who gave the first example? Who gave the first example?
So,
It was
Amit,
3 square plus 4 square equal to 5 square. Can you see any similarity between these two?
my,
So it is like 3 into 2, 4 into 2, and 5 into 2.
Can you see? Yes. So everything is multiplied. Can you give any other pair? Any other pair?
So
Will
12,
this have
16 or 20.
12? Okay, 12 square plus 16 square equal to 20 square. Have you checked this? What is 12 square? 144. What is 16 square?
256.
256. And what is this is 400. So this is. So can you see the relation between these two? How much is this? How much is this? And how much is this?
Sir, again into 4 multiplied by 4.
So multiplied by 4. So you can also multiply it by 3 and so on. So by this way, you can construct maybe infinitely many such pairs, so which actually satisfies this property for an right angle triangle, right? So it is 3, 4, and then it is 5. And then it will satisfy this. So for a square plus b square equal to c square, there exist infinitely many such a, b, c satisfying this property. Okay. Now the question is, what will happen if this is the case and this n is strictly greater than 2? Okay. Then Fermat, for the first time when he was studying that book, so this was the book. So this was the copy of that book. Okay. And Fermat always made some comments on the margin of the books. So usually what we do on an exercise book, we write it here, but Fermat, he had a very peculiar kind of habit that he always makes some comments on the margin of the books. Okay. So he stated this result, that there exists no positive a, b, c, which are natural numbers and which satisfy this equation if the value of n is greater than 2. Okay, he just stated this result and he told that, okay, I know the proof of this result, but I don't have much space on my margin so that I can write down the proof of the result. So he just stated this result, and then it was all there only on his book's margin. So he told that I know the proof of this result, but due to the space constraint here, in only this much space is there, I am unable to write the proof of this result. And after his death, his son actually revealed this result, and he made it a kind of publicized it. Okay. And you will be surprised to know that, so you can understand that it was stated around 1637. And it took more than 300 years, around 1994, it took more than 350 years to prove this result. And you will be surprised to know that the whole mathematics community was actually divided into two parts, because he claimed that there exists no such ABC. So one group of mathematicians, they thought that, okay, his result is false. As a result, they wanted to find some ABC so that this equation should be satisfied. And another group of people, they thought that, okay, Fermat's results were correct because he has given a lot of results which he didn't give a proof, but all the results became correct. Almost all the results became correct. So many of the mathematicians, they believed they believed Fermat, and they tried to prove it that, okay, there does not exist any such ABC. But none of the mathematicians before 1994 could able to solve this problem. And one of the reasons that why ring theory is there is due to only this statement of this problem. So many new topics of number theory, like algebraic number theory, geometric number theory, all these number theories branches came only due to this problem. And ring theory is considered to be one of the byproduct of this problem. Okay. So many of the mathematicians, they actually got mad. Whole life they spent to solve this problem, but they unable to solve this problem. And at the end, they came with no conclusion. But it's for the first time in 1993. So it is again a very interesting history about Andrew Wills. So you might have heard about Manjul Bhargava, who was the field medalist. So Andrew Wills was the PhD guide of this Manjul Bhargava. Okay, so in June 1993, Andrew Wills presented his proof to the public for the first time at the conference of Cambridge. So he was actually given a lecture at Cambridge University in 1993. So he didn't declare that he had given a proof of Fermat's last theorem. He just started solving some problem, and it was a 2-day seminar. Okay, so he was given a lecture for 2 days. So the title of the talk was Modular Forms, Elliptic Curves, and Galois Representations. So he didn't give any kind of clue that he is going to give the proof of Fermat's last theorem. But when he ended up his theorem, he told that that's the proof of Fermat's last theorem. And people were stunned to see the proof. And it was like a sensation at 1993. And many mathematicians, they now came to know that it was a solve of after a 3050 years, more than after 3050 years. But so it was in June, but in 1993 August, so June, July, August, Andrew Wills itself found a mistake in his proof. Now again a strategy. So he finally found some error in his proof. But fortunately, he with one of his students finally in 1994 came with a corrected proof, and till now this is considered to be a correct proof of Fermat's last theorem. So starting from the very beginning of this Fermat's last theorem, it is really a sensational one, and at the end of around 1994, people came up with a correct proof of Fermat's last theorem. So in our class, we'll also talk about not about the proof of this Fermat's last theorem. You can understand that it's not really very easy to follow this proof, but we'll certainly talk about a particular problem given by Fermat, which is known as Fermat's little theorem. That's also very interesting and had a lot of applications in today's cybersecurity. Okay. So there are plenty of very cute looking statements in number theory. Like this Fermat's last theorem, the statement is not very difficult to understand. Even a class 7 student can understand the meaning of the statement. So that's the beauty of number theory. So if you look at this number theory, you'll find that there are plenty of very cute looking statements there which are still not solved. So people are still trying with lots of computers, lots of mathematical knowledge, but still they are not solved. That's why number theory is one of the favorites, because from the very childhood we deal with numbers. So it's very close to our heart, but there are very cute looking statements are there which are still unsolved. For example, this conjecture given by Goldbach. So Goldbach in 1742, he wrote a letter to Euler. So in today's talk, I will also talk about few works of Euler. So he wrote a letter to Euler in which he proposed the following conjecture. What is so? It was his original handwritten that letter. So it says that Goldbach conjecture. It says that every even integer greater than 2, every even integer greater than 2 can be expressed as sum of two prime numbers. So every even integer greater than 2 can be expressed as sum of two prime numbers. For example, 32 can be written as 3 plus 29. But the question was, is it always true? So he was given a conjecture. That means he was unable to prove. Just he gave a statement to Euler that I found an interesting result that every even integer can be expressed as sum of two prime integers, two prime numbers. So now I am going to show you. Can anybody tell me any even integer? Any even integer? Let's try with any even integer. Anybody?
6.
6. Okay. Okay, 6, you can see that 6 can be written as 3 plus 3. Any bigger one? Maybe 60. You can
Sir,
see that,
42 equals to 5 plus 37.
yes, but give me any even integer, like
224.
224. You can see that there are plenty of ways to write it down. 13 plus 211, 31 plus, like this. Any bigger number if you want?
1000 and 1056.
1056. You see that if the number is bigger, the list is even bigger. So there are plenty of ways to, all of them are prime. So this is one prime, this is another prime, this is one prime, this is another prime. Anybody will try with some bigger, even bigger number? So I just put 10 maybe here. You can see that that can also be written in this way. So the list is going bigger and bigger. Okay, so there are plenty of ways. And you will be surprised to know that not yet anybody could able to prove this, but with the supercomputer event, people had tried with big numbers and still the result is true. But nobody came up with any formal proof whatsoever. Whatever big number that a computer can uh, compute has been checked with that number, and still for that number this result is true. But unfortunately, anybody couldn't come up with any formal proof of this till date. Okay, so I request all of you to have a look at this, and there are plenty of other problems are also waiting for you. And in number theory, it happened many times that many of the problems are solved by young students, because when the number theories, they know many things, but when they try to solve this, what happened that they always try to put some big or very complicated mathematical results. But it happened that sometimes the results could be proved by using very simple technique, which usually come from a very maybe undergraduate student or maybe school students. So without owning anything, just try to prove the result by using whatever you know. Try to solve or try to have a look at this, and there are plenty of such mathematical number theoretic results are there which are still open. There is another, it's known as twin prime problem. So somebody's mic is okay. So there is another problem known as twin prime problem, which also it's very easy to state. It says that the primes which are at a difference between two primes, for example 3 and 5, so there is only one integer in between, even integer, like 11 and 13, so only 12 is there. So this kind of primes are known as twin primes. For example 137, 139, they are twin primes. So you can see that there exist plenty of such primes, twin primes, but it is still a conjecture that there exist infinitely many twin primes. So it was proved that there exist infinitely many prime numbers, but still it's not proved yet for this form that there exist infinitely many twin primes. Okay, people whatsoever they tried with very big numbers, and they always could find some pair of this kind of primes, but still analytically or mathematically nobody yet could able to prove that there exist infinitely many twin primes. On the contrary, I can show you a very interesting result. So if you tell me, if you give me any number, say for example, say if you say any number, whatever big it may be, suppose you give me n, which is greater than 1, okay? So I can always construct a sequence of numbers, consecutive numbers. For example, I consider say m1, m2, up to say mn. So they are all consecutive numbers. So this is say m1, m2 is m1 plus 1, and so on. So this is mn is m1 plus say n minus 1. Okay, so they are n consecutive numbers. Whatever big n you will give me, I can always construct this n consecutive numbers so that none of these numbers are prime. So nobody in between. So from here to here, these n consecutive numbers will not be prime. That means there exists an arbitrary long gap. I can always construct such a gap in which there will be no prime in between these two numbers. That means suppose you give me 100 or you give me, so I can always find some n and say n plus 99. So they are 100 consecutive numbers so that no prime is there in between. That means there will be a long gap between these two numbers. So you may think that, okay, 100 may be very small. So why not then 100 to the power 100? So this would be a very huge number, but still I will able to find some n and n plus 100 to the power 100 minus 1 such that, so it's a huge number, huge long range of numbers, and there will be no prime in between. Okay, and that's a quite a anti-intuition between this problem that there exists infinitely many twin primes. So you know there exist infinitely many primes, but this results state that there exists no prime in between whatever big n you can give. I can always find n consecutive integers such that no prime will exist in between that range. And fortunately, this result is not very difficult to prove. You can very easily understand the proof of this result. The proof is like this. You just consider n plus 1 factorial plus 2, n plus 1 factorial plus 3, and so on, n plus 1 factorial plus n plus 1. So you can understand that this number is divisible by 2, this number is divisible by 3, and this number is divisible by n plus 1. So you can find that there are n consecutive numbers. Every number in between, I mean, if you consider from here to there, then you find that every number is divisible by some of this n or something. That means none of them are prime numbers. So number theory is very peculiar. Somewhere you will find infinitely many such. If you consider this to be a number line, if say 0, 1, 2, and so on, then you can always find a arbitrarily large, whatever big that you want, within that range you cannot find any prime in between, whereas there exists infinitely many primes. That has been already proved. So it's very peculiar and very interesting. That's why many people, they jump to work on number theory, but the problem is number theory looks very simple. Many people, many students can understand it very easily, but it's really very difficult and very tricky to prove. Once you know the result, once you know how to prove this, you will find that, okay, that's very easy. But it may not be always the case that very simple tool could be used to solve lots of problems. Okay, so I'm not going to much details about very interesting topic is this number theory, and there are plenty of such nice examples are there with me. But for the time being, I want to skip that part, but instead I just want to show you a few of the applications of number theory. For example, we are very much required with this cyber security. So I'll just go to here. Yeah, so cyber security is one of the places where number theory is heavily used. You'll be surprised to know that. In this class, I will try to show you how cyber security and number theory are related. So this is an example of a prime number. You can see that this is 904 digit long prime number. So just looking at this number, you won't be able to judge whether this number is prime or not. But believe me, this is a prime number, and this prime number can be constructed or generated very easily by using this small laptop, by using this software that I have used. For example, this one, Sage. So you can see that the whole thing is a prime number. Okay. For example, if you try with this, so next prime, say 100. Let's give you 101. Put, you can see that how fast it is to give you the number. Okay, so maybe little bigger. Yes. If you're not happy with this many zeros, gives you the answer very quickly. Or maybe you can put many more zeros very quickly. So this is 2 to the power 3000. Can you believe this? 2 to the power 3000. And it consists of around 1000 digits. So it consists around 1000 digits. And it took around maybe, it takes little more time. It took around maybe 2 minutes to give me this big primes. So this software is very easy to use, and this is known as Sage Math. Maybe some other point of time, if I have some courses on Sage Math, I will able to show you how interesting is this. And for example, suppose you want to construct factorial, say factorial. So how big factorial you have seen? Anybody? Any number that you want to give? Any number? Of course, it has to be quite decent. You cannot give, for example, if I put 2, it will give me 2. If you put 20, and it is this. So for those who are studying for this competitive exam, sometimes it is asked the question that how many zeros are there at the end of this 20 factorial or 30 factorial or maybe 70 factorial. So that is very easy to calculate. Anybody, how can you calculate how many zeros are there at the end of 20 factorial? You can see that there are 4 zeros, but how to calculate this? Anybody?
Sir, 0 of 20, 0 of 10, and 0 of 5 and 2.
0 of 5 and 2 means?
5 into 2, 10.
Okay. So one thing you note that 220 means it basically is 20 means 20 factorial means it's 2, 1 into 2 into 3 into ... 20. Okay. Now at the end the 0 will appear only when you will have 2 and then product of 5. So only this pair will give 1 0. Okay. So the question is, how many 2s and how many 5s are there in 20? In 20 factorial. Okay. So the idea is you can see that the number of 2s will be quite less quite more compared to number of 5s in 20 factorial as a factor. So you can very easily understand that how many factors are there which has 5. Like 20, you will have factor will come from 1 factor from 5 it will come, 1 factor will come from 15, 1 factor will come from 10, another factor will come from 5. And there are plenty of 2s are there. So 2 are there within 20, within 18, within 16, within 14. So there are plenty of, at least more than 5 factors of 5s are there. I mean, more than 4 factors of 2 are there within 20 factorial. So it is sufficient to count the number of 5s that are present as a factor within 20 factorial. So you can see that there are exactly 5 places where this 15, where this 5 comes. That's why at the end it is only 4 things. Now if I put it like quickly, can anybody tell me how many zeros will be there at the end of 100 factorial? So by your calculator, you won't be able to see what is 100 factorial. But quickly, can anybody tell me by doing the mathematics how many in 100 factorial, how many zeros will be there?
20.
How did you calculated it? So 100 factorial, how did you calculated it?
It's 100 by 5.
100 by 5 will be sufficient? Anybody? So do you think that it will be 20? 20 zeros will be there? Anybody? Any other answer?
Sir, 24.
Okay, somebody gave 24. So it will be, the answer will be like this, plus 100 divided by 5 square plus 100 divided by 5q and so on. So what is this number? So this is 5 to the power 1. What is this number? This is basically the box function. You know what is box function? For example, say 10 by 3. What is this box? The greatest integer not exceeding this. So 3 point something. If say 5 divided by 2, how much it will be? 2. Okay. So you can see that this is 20 and this is 25. 100 divided by 25, this is 4, and this is 100 divided by 125. So this is 0 basically. So 0 and so on. After that it will be 0. So altogether 24. So just have a look at this. Let's see how many of them. Okay. Try to calculate it carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So we are done basically. So the number of zeros of n factorial, the formula is like this. So the number of zeros of n factorial, number of zeros of n factorial is, of course, n should be greater than or equal to 2 maybe, or yeah, is n divided by 5 to the power 1 plus n divided by 5 square plus n divided by 5q plus and so on. So you can understand that very soon the denominator will exceed the numerator. As a result, that term will become 0 and whatever be the answer. Now quickly tell me how many zeros are there maybe with 60 factorial. Quickly, how many zeros are there with 60 factorial? Quickly.
Sir, 40.
40.
40. 1/4.
Oh, 1, 4. 14. Okay. So let's see. 5 means 60 divided by 5 plus 60 divided by 25 and rest are 0, right? So this is 12 plus this is 20 means 2. So 12. Okay, sorry, 14. So let's cross check. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's check. Our answer was 14. Now it's clear to all of you. So if this kind of question will appear in your competitive exam, now I guess it will be easy for you to solve this problem. Okay. So these big primes are very important. So now you can understand that it's very easy for us to find these big primes, and you will be surprised to know that simple algebraic techniques, mostly the concepts of group theory, are used to find these big primes. And that is one of the method to solve this problem is known as Solve-Strachan probabilistic primality testing algorithm. And that uses very simple group theoretic techniques, which are basically law of quadratic residues and all, which are not very difficult to understand. But if you're interested, you can just have a look at the number theoretic classes of mine posted in my videos. There you will be able to see how this probabilistic primality testing algorithm can be done very easily without not knowing much about very big concepts of number theory. You can do it very easily. Anyway, so these big numbers are not very difficult to find whether the number is prime or not, and these big numbers are very much required while we are getting the cyber security. For example, in today's scenario, you see that Google provides a lot of free things. Like you have Gmail, you can have YouTube, you can make a Excel sheet, you can have a calendar, you can talk with others, you can do meeting, Google Meeting, the meeting that we are now conducting. All the things are being done very easily by Google. And while doing so, Google requires these big prime numbers. And in my class, I will try to explain why and how these big prime numbers are required in Google. Okay. So not only that, many times we do online transaction, right? You do a lot of online transactions, especially during this lockdown period or during this pandemic situation. You have to buy many things online. Okay. So the question is, when you connect with something with your server or something, then you are basically, say, pay something by using your credit card or debit card. So you know that you have to take care of some payment gateway. So there will be some third party who then contact with your bank. So the money has to be deducted from your bank account, and then it has to be paid to the merchant. For example, suppose you are at your home or even maybe at a shopping mall, then you pay by using your credit card or debit card. Though these two guys are very nearby, but it takes many routes to get the money. For example, first it will go through some payment gateway, then some third party will be there. It will then connect to your bank account details and checks whether sufficient amount of money is there or not. And if you have legitimate amount of money to pay the merchant, then only the money can be transferred to the merchant accounts. So while doing so, lot of things, lot of securities needs to be incorporated. Otherwise, many people may steal your information, and they can also do the same thing to buy things from your account by using your credit card details. But that is not usually the cases. That's why we are very fond of using our credit card or debit card. Sometimes you might have seen that WhatsApp are using end-to-end encryption, and there also they require the big prime like this. In our class, we'll try to mention how this big primes could be useful in getting the security of WhatsApp. Okay. So when in today's scenario, we use many things during this pandemic period, we use from our home, we buy many things using our credit card or debit card or UPI apps and something. Okay. One of the very simple way of doing a fraud on your online banking system is that many times you get phone calls from some bank agency, and it says that you will be getting free credit card, or you will get some reward points, etc., if you use this. So if you talk with them, they are very convincing, they are very fluent, and they are very good in making you understand that okay, they are the genuine one, and they are calling for your own sake. Okay. Then suddenly they will ask you, okay, during this pandemic period, you do not need to come to the any bank branch. Just I will send you one link, and you click this, and that will be fine for you to have the credit or have the credit card or maybe the rewards. So what they do, they will just send you a link, and you will be surprised to know that many customers, or many, especially the young generation students, they actually click on that link. What usually they send on that link? They usually send a link for a very powerful software. Many of the cases, it is known as Team Viewer. Okay. That means that powerful software is mostly used to get access of your mobile from a remote place. For example, I am sending you a link to your mobile. What it says, when you click on that link, some software will be installed, and then some OTP will be generated, and it will be sent to your mobile. Then the bank guy, who is actually a fraud guy, will ask you, okay, see, some OTP has been generated, we send you a OTP. For verification purpose, you need to give us the OTP, the 6-digit or maybe the 4-digit number. So when you give me the 4-digit number or the 6-digit number, I will enter it into my mobile or into my laptop or into my desktop. that OTP actually gives the consent that you are giving the consent of accessing your mobile. That means that OTP actually kind of consent from your side to me that you are giving the permission to access your mobile. When the OTP, I will just put the OTP onto my machine, then I will have the access of your mobile. What do you mean by the access of your mobile? I can see your screen, I can read your message, I can see your photos, all the message I can do. Not only that, I can even operate your camera as well as your microphone. Now think about it. If somebody is operating your camera as well as your microphone without your knowledge, then what may happen? And that is happening. So then what they will say? They will say that just do some 10 rupee online transaction to the bank, and then the reward point will be delivered, because it will be a kind of verification of your bank account, etc. Then what you will do? You will on your UPI app, or you will put all the bank details, the credit card number, etc. onto your machine, onto your mobile. Since I am the full control of your screen, I can see everything. Then it is actually a transaction to your bank, and some OTP will be generated from the bank, and the bank will send you the OTP. Since I can also read your message, I can also check the OTP. Now suppose you pay the 10 rupee to that bank. It is genuine payment. But what is happening, since you are opening your UPI app or maybe the whole card details, I see everything. Then after getting all the information, what I am going to do, I will pay, or I will take out all the money, or I will buy something from your account by using your mobile from my laptop. I will buy things and you are going to pay it. And then you will find that 3 or 4 consecutive OTP will come to your mobile, and every OTP it says that, or every message it says that your bank, your this amount has been deducted from your account, and you will get 3 to 4 consecutive message. Within 3 to 4 messages, all the money of your account will be gone, because I know I can see the OTP. Then when I see the OTP, I'll just put the OTP there and the money will be deducted from your account. So that's the very important way of hacking nowadays. So you'll have to be very careful. One thing, if you're cautious enough, then it will be sufficient that till now, no genuine agency will ask the OTP through mobile or through phone. So usually the OTPs needs to be put either into some website or into some apps. No genuine company will ask your OTP through phone. So if you are cautious enough, then it is very easy for you to check this kind of happenings. Another thing is that when we buy something using our credit card or debit card, using say Amazon or somewhere, then you see that some HTTP and then something is there. Mind that you always have to check whether this is HTTPS or not. If it is only HTTP, then it is recommended not to use that site for any online transaction. So HTTPS is always there for you to save at least this kind of happenings. Another thing is also very important, that is you must update your phone. So sometimes it happens that some older version of your software is there. So I am not saying that whole phone should be updated, but the browser has to be updated. Okay, so if sometimes if you update your phone, then it becomes slow. So sometimes it may not be a good idea to update your older version of your phone, then it would be very slow. But always be updated on which you are trying to buy things. For example, if you're going to use some apps, then you should first update that apps for buying things. One another warning is that for most of the online shopping kind of organizations, they do have the, if it is a genuine one, they do have some kind of phone number where you can give some feedback to them, or may some complaint, may some lodge some complaint to them. For fraud websites, usually it is the case that they put some arbitrary phone number, or even the phone number may not work. So if you see some of the website which you think that that may not be a genuine one, then just have a look at the phone number, you make a call there. If somebody will pick up the phone and give you the quite genuine answer, or if some automatic voice will be generated, then you will be at least have some confidence that okay, with the site that you are now going to talk is a genuine one, may not be a fake one. So if this kind of things, if you remember all those things, then it is really difficult for the hackers to get into your phone. And remember one thing, that most of the cases this hacking things are happening due to the ignorance of the users and not from the system's viewpoint. Most of the cases the systems are nicely generated, but most of the cases the users, they actually on their own give all the details of their own for the sake of some getting some reward points, etc. That is for the most of the cases. Now in this class I will try to show you how the number theory and abstract algebra plays the most important role here. Okay, so for that, let us have a look at few of the interesting number theoretic techniques. For example, we already heard about Fermat's. So there is very famous theorem known as Fermat's little theorem, not the Fermat's last theorem. Fermat's little theorem. Okay. So anybody maybe tell me any number between 1 to 4. Choose any number between 1 to 4. Anybody?
2.
2. Okay. So 2 to the power 4 and then divide it by 5. 2 to the power 4 mod 5. What is that value? What is that value? 2 to the power 4 modulo 5?
1.
1. Very good. Okay, now let's check 3 to the power 4 modulo 5. What is this value?
1.
Again 1. Oh, surprising. Okay, let's check 4 to the power 4 modulo 5. What is
1.
this value? Again 1. Oh. And of course, 1 to the power 4 modulo 5 is again 1 modulo 5. So there must be something interesting here in 5. That's why it's happening. Okay, let's check with maybe 7. Now let's choose any number between 1 to 6. Anybody? Any number between 1 to 6?
5.
Okay, 5. Let's 5 to the power 6 modulo 7. Anybody quickly? Can anybody give the answer? What is 5 to the power 6 modulo 7?
1.
Okay, so you calculated it or you just used some result?
Sir, use the result.
Okay, you use the result. You can check this. Okay, my software can do it very quickly. So if I like this, if I do this mod 5 7 to the power 6 gives me the value 1. Okay, so instead of 5, why not 4? Then also you see that 7. So instead of 3, let's check. So it's 3 to the power 6 modulo 7. It's also given 7. So let's then try with any prime. So give me any prime number you want. Any prime
13.
number? 13.
13.
Okay. Okay, 13. Then I need to put it 12. So take any number from 1 to 12. Any number between 1 to 12.
7.
8.
Okay, let's put 7. And that's also giving 1. That's quite crazy. Okay, so what is actually giving? And that's the Fermat's little theorem. It says that let P be a prime integer and A be an integer such that P does not divide A. Then A to the power P minus 1 is congruent to 1 modulo P. See, Here, all the things that I am doing is here, this is P and 1, 2, 3, 4. In case none of them are being divisible by 5, so a to the power p minus 1, that's why a to the power 4 is congruent to 1 modulo p, 1 modulo p. In case of 5 and 7, so 7 does not divide 5, that's why 5 to the power 7 minus 1, that is 6, is congruent to 1 modulo 7. So that's Fermat's little theorem, and it has lots of application in real life. Let's have a look at the proof of this. So you could have proved this by using, say, number theoretic technique, but I'll give you the proof using very simple technique, group theoretic technique. So the proof, okay, consider Z P star, okay. Then what is the order of ZP star? What is the order of P minus 1? So as P does not divide A, class A, where it should belong? So if P does not divide A, what does it mean? GCD of AP is how much?
1.
Is 1. Then class A must belongs to where? Class A,
P star.
ZP star. And you know that if you consider any element and if you make a power of the order same as the order of the group, then what you will get? So this is the group of order p minus 1, and this is an element of that group, and you make a power up to p minus 1, then what will get?
1. Identity.
This is identity element you will get. And what does it mean? In case of a class, that implies a to the power p minus 1 is congruent to 1 modulo p. Why so? Because if you make it little longer, then it will be clear to you. I guess all of you might have understood this, but still, if not, just make a change of this. A to the power p minus 1 minus class 1 equal to class 0. That implies a to the power p minus 1 minus 1 is class 0. What is class 0? That is same as 0 mod p, right? So this is divisible by p. So that means p divides this, and since this is equal to this, that means p divides a to the power p minus 1 minus 1. Then what does it mean? This implies a to the power p minus 1 minus 1 is congruent to 0 mod p. And what is then, if you just make a side change, what that will be giving you? P minus 1 is congruent to 1 mod p. So any question? Understood all the steps? Is it clear to all of you? Or shall I repeat? Is the steps clear to all of you? So from here, it's basically, this is for extra, why this is congruent to 1 mod this. Is the result or is the idea clear to all of you? Any question or any doubt? Anybody? Anybody has any question? Can you see me?
Yes,
Yes,
sir.
sir.
Is it clear to all of you? Is it clear?
Yes, sir.
Yes, sir.
Very good. So now you can understand that how to prove this. Okay. Well, now I will come to the result of Euler. So Euler's theorem. What it says? Let n be a positive integer, say greater than equal to 2, and a be an integer such that GCD of an equal to 1, then a to the power phi n is congruent to 1 mod n. So you all know what is Euler phi function. So what is Euler phi function? Do you remember the definition? What is Euler phi function? Number of positive integers less than equal to n and relatively prime to n. Okay, for example, if we consider phi of 6, what is phi of 6? Quickly. So this is the number of positive integer less than equal to 6. That means who are there in the set? 1 is there, which is relatively prime to 6. 3 is not there, but 5 is there. So the cardinality is 2. Right? So what is phi of p? Anybody tell me what is phi of p, where p is a prime?
P minus 1.
P
P minus 1.
Very good. So p minus 1. I have already shown you, right? What is phi of p to the power n minus 1?
P to the power n minus p to the power n minus 1.
I have shown you the proof.
Yes,
You
sir.
remember? You remember the proof? I have already given you the proof. But interesting property is that if, so I'll come to the proof later on, but before that, let me give the interesting property about the fact about phi n is that if GCD of mn equal to 1, where mn are greater than equal to say 2, then phi of mn equal to phi m into phi n. This is known as multiplicative property. Multiplicative property. So I can put it greater than equal to 1. I think that will be sufficient. Okay. If m and n are relatively prime, then, and the converse is also true. The converse is also true. So this is an if and only if result. And it can be proved very easily by using group theoretic techniques. And that's why I told you that number theory and group theory are very important. For example, how this result is playing an important role. For example, suppose I want to find what is phi of 1000. Now, if you go by this definition, the number of integers which are less than equal to 1000 and relatively prime to 1000, you will find that it would be very difficult to get the answer quickly. But fortunately, we have this result. So first we make it in a product form of primes. So this is 2 into 5, but some powers are there. Can anybody quickly tell me what would be the power? 2 in 2 to the power something into 5 to the power something. Tell me what are the powers? What are the powers? 2 to the power how much and how much 5 to the power this in 1000? Quickly.
3.
2 to the power 3 and then 5 to the power
3.
5 to the power 3. So that is phi of, since 2 to the power 3 and 5 to the power 3, they are relatively prime. So by using this result, you can have 2 cube into phi of 5 cube. And now you can apply this result. So this is 2 cube minus 2 square and then 5 cube minus 5 square. And how much is this?
400.
This is, yes,
400.
so this is 4 and this is your 25 minus 125 minus
100,
25.
400.
So 100. So this is 400. Now you see that by using this formula, this is very handy and very important formula for many competitive exams. So very easily you can do that. Now the question is how to prove this result, and that proof is also very easy. So now we are going to prove this result by using group theoretic techniques. You can also prove this by number theoretic technique, but that will be little longer. But you know that if, okay, Zmn is isomorphic to Zm cross Zn when, if and only if, what should I write it here? If and only if, what should I write? Yes, very good. If and only if GCD of Mn equal to 1. So that you already know from cyclic group property. Okay. Now, how many generators are there here? How many generators are there for Zmn? How many generators are there? Pi of Mn. Very good. How many generators are there here?
Phi of m.
Pi of m. And how many generators here is phi of n, right? Now you need to just give a kind of connection between this. Now this result is quite obvious that if, say, class A is a generator of Zm and class B is a generator of Zn, then class A comma class B is a generator of, whose generator? Class A comma class B is a generator of
Zmn.
Z, not Zmn, but Zm cross Zn. So how many generators are there in this? How many generators are there? The number of generators here into the number of generators here. For example, if I consider, say, Z12, okay, so that is isomorphic to Z2 square into Z3. So how many generators are there? We know that class 1 is a generator, class 3 is a generator, and here two generators are there. Class 1 is a generator, class 2 is a generator, right? So how many total generators are there here? How many total generators? This one along with any two of them will be a generator. This one along with any two of them will be the generator. So there will be here two options, here two options. So altogether four options. That means class 1 comma class 1 is a generator, class 1 comma class 2 is a generator, class 3 comma class 1 is a generator, class 3 comma class 2 is a generator of whom? Generator of Z4 cross Z3. So you see that the number of generators here was 2, the number of generators here was also 2. As a result, the total number of generators were 4. 2 into 2, 4. Since this group is also isomorphic to this, so algebraically this group will also have the same number of generators. So this group will also have 4 generators. Now come to the original problem. There, now it will be quite clear to all of you that here, so in this group, the number of generators were, how many generators will be there in the cross? How many generators are there? Put some notation here. What should I put it here? What should I put it here? This has phi m many generators, this has phi n many generators. So in the product, how many generators will be there? What should I write here? Anybody?
Dot.
Dot. That means multiplication. So altogether, this many generators are there in this group. Since this is isomorphic to this group will also have the same number of generators, but we have already calculated the number of generators were phi mn. So what should I write it here? They must be equal. So since this was an if and only if result, so this, the converse is also true. The converse is also true. So this is also an if and only if result. So now you are done. So by using this group theoretic technique, you can prove this result very easily. But if you look at any number theoretic book which proves it by using the classical number theoretic method, that will take maybe more than 2 pages. But here you are just using all your known results about group theory, you get the answer very quickly. Is the proof clear to all of you, or shall I repeat once again? Is the proof clear? Okay. So I assume that you understood this proof. Now we come to the main result. What it says? It says that if GCD of n equal to 1, then a to the power phi n is congruent to 1 modulo n. Let's come to the proof. And the proof technique is almost same as Fermat's little theorem proof. Okay, so let me write it once again. The theorem, it states that let n be an integer greater than equal to 2 and a be an integer such that GCD of an equal to 1. Then a to the power phi n is congruent to 1 modulo n. Now I am going to use the same proof technique as Fermat's little theorem. So what should I consider here? Which group should I consider here? Which group should I consider here? Anybody? To prove this, which group should I consider?
Sir, UN.
Very good. So UN, that means Zn star. So consider this. Then how many elements are there? Then order of Zn star is how much? Phi n. As GCD of An equal to 1, then class A will belongs to Zn star. Then just like Fermat's little theorem, a to the power order of the group is phi n equal to class 1, and that implies, as just like my previous steps, a to the power phi n minus 1 equal to class 0. What does it mean? That n divides class 0, that means n divides this. That implies n divides a to the power phi n minus 1. That implies a to the power phi n minus 1 is congruent to 0 mod n, and that implies a to the power phi n is congruent to 1 mod n. That's all. The same proof as Fermat's little theorem. Now can anybody, is it clear? Is the idea clear to all of you? Good. Now let us have a look at Fermat's theorem. So what was Fermat's theorem? It was n was p, right? And then it says that p does not divide a. So if p does not divide a, that means GCD of ap equal to 1. So you see here the integer n was greater than equal to 2. So in that case, p is my integer, which is of course greater than equal to 2, and GCD of an, that means ap equal to 1. Then by Euler's theorem, we could have a to the power phi of p is congruent to 1 mod p, right? By Euler's theorem. Then what is phi of p? Phi of p, if p is prime, what is phi of p? A to the power, tell me quickly, a to the power. Phi of p is how much?
P minus 1.
P minus 1, congruent to 1 modulo p. And that's the Fermat's little theorem. So you can understand that Euler's theorem is a generalization of Fermat's little theorem. Okay, and based on that, lots of important things could be done. So there is another important function which is known as number of positive divisors function. So that is denoted by tau n. This is number of positive divisors of n, where n of course greater than or equal to 2, and tau n is sum of positive divisors of n greater than or equal to 2. Okay. Now the question is, can quickly tell me how could we, what should be the value of tau of 7? Tau of 7, can quickly tell me what is the value of tau n? This is number of positive divisors of 7. What are the positive divisors of 7? 1 and 7. So this is 2. What is tau of 11?
2.
2. What is then tau of p if p is prime? What is, if p is prime, then what is tau of p?
2.
2. Very good. Now what is tau of p to the power n? What are the positive divisors? You can see that the positive divisors are 1, p, p square up to p to the power n. So how many? N plus 1. So tau of p to the power n is n plus 1 if p is prime. Okay. Fortunately, tau also satisfies the multiplicative property. That means tau of mn equal to tau of m into tau of n if and only if GCD of mn equal to 1. Okay. Now can you very quickly tell me what is tau of, say, 50,000? Quickly. Very easily now you can calculate. Tau of 50,000. In JAM exam, you have to calculate this kind of numbers. So very frequently this kind of numbers are asked in JAM. Quickly.
So 30.
Okay, tell me what is this value, 50,000, how do you divide this? So 2 to the power
4 and 5 to the power
Sir,
5.
5 to the power 5, 2 to the power 4.
2 to the power 4, 5 to the power 5.
Yes, sir.
Yes, then it will be 4 plus 1 into 5 plus 1, that is 30. Very good. So now you can understand that whatever big it may be, if you are able to break it in terms of this prime factors, then you are basically done. Then you are able to find these values very easily. Now what would be the sigma of p? What is that sigma of p? It is the sum of positive divisor, that is 1 plus p. What is sigma of p to the power n? This should be sum of positive divisors. So here you can see that sum of positive divisor will be 1 plus p square plus p to the power n. Can quickly tell me what is this value? P to the power, what is this value? What is this value? Quickly, the formula.
P to the power n minus 1 by p minus 1.
P to the power n minus 1. Are you sure?
Sir, p to the power
No, p to the
n
power n minus
P to the power n.
minus 1.
p to the power n minus 1 minus 1.
This one.
No, sir. No, sir. P to the
Then
power n minus 1.
what is p to? Tell me first again. P to the power. So you forget this formula. Oh.
Sir, sir, P to the power n আর minus 1 টা স্যার আলাদা।
P to the power n minus 1 like this.
Yes, sir.
Is it correct? Tell me how many terms are there?
No, sir. P to the power n plus 1 minus 1 by p minus 1.
Yes, now it's correct. So p to the power n plus 1 minus, because there are n plus 1 many terms are there. So you told the formula for n terms, but here I have given n plus 1 terms. So this will be p to the power n plus 1 minus 1 divided by p minus 1. And again, fortunately, this is also a multiplicative function. That means sigma of mn equal to sigma of m into sigma of n if and only if GCD of mn equal to 1. Okay. Now quickly tell me what is the value of sigma of 100? Quickly. Sigma of something into sigma of something. So 2 square into 5 square. Now give me the value quickly. What should I write here? Even you can do it very easily like this.
217.
217.
1 plus 5 plus 5 square. Yes, how much is that?
217.
217. This
Yes.
one?
Yes.
Okay. So everybody agrees with this? Okay, very good. So now you understand this. And this proof is there in my chapter 10. In my book, if you go to the chapter 10, then the proof of this, why their multiplicative function is given there. Okay. So you can have a look at that from chapter 10 of my book. There you will find the details of the proof how to show that these two functions, tau and sigma, are multiplicative functions. For example, if I ask you the question, can you tell me how many subgroups are there? Very frequently this kind of questions are asked in JAM. How many subgroups are there for Z 100 plus? Anybody?
The tau of 100.
Very good.
Yes.
So in case of a cyclic group, the number of subgroups are, you can very easily find for cyclic group, the number of subgroups are basically the number of positive divisors. So for each positive divisor, you will find exactly a subgroup, and that subgroup is unique up to isomorphism. So it is sufficient to find the value of tau of 100. And what is that tau of 100? Quickly, what is tau of 100? What is tau of 100?
9.
9. So tau of 2 square, tau of 5 square, and that is 3 into 3, this is 9. Now you can see that in JAM exam, if you are going to find all possible subgroups by hand, so E is a subgroup, like class 0 is a subgroup, this is a subgroup, so you already find 2, and then why not then class 0, class 50 is again a subgroup. And then if you want to calculate by this, then you can understand that if I give you the number like this, instead of 100, if I ask you the question with 50,000, then you will be lost soon. But just now you see that how to calculate this very quickly. This value was 30. So very easily you can say that, okay, there exist exactly 30 subgroups of Z 50,000 plus, very easily. So that kind of problems are very common in JAM exam. So you need to remember all those things, and I have given a problem set of number theory as well that will also be helpful for you in understanding those things. Another important problem or another important theorem is Wilson's theorem. What it says, if P is a prime, then P minus 1 factorial is congruent to minus 1 modulo P. If P is a prime, then P minus 1 is congruent to minus 1 modulo P. Sometimes it is asked that when, say, 90, say, when 100 factorial is divided by the prime 101. So other way around. Question is, what is the remainder? What is the remainder? Remainder when 101 divides 100 factorial. So you can understand that it's not very easy to calculate 100 factorial, because the value of 100 factorial would be something like this. So factorial, so already we have seen that 100 factorial is how big. So if you want to calculate this, and then if you want to divide it by 101, then you won't be able to complete your at least any other problems that are asked in your question. But there are other ways to do so, and you can use this one. Now tell me, what is the remainder quickly? What is the remainder? What would be the answer? Anybody?
So 100.
Very good. Don't give minus 1, because minus 1 can never be a remainder. So you can write it like this. As I mentioned, if something is negative, then just add the P. That will give you the positive value. So that is same as P minus 1 modulo P. And P minus 1 is a positive integer which is strictly less than P. And in that case, P minus 1 will be 100. So 100 factorial is congruent to 100 modulo 101. Okay, sometimes that is asked. In my previous classes, did I show you how to find the inverse of an element? Did I? By using extended Euclid algorithm? Extended Euclid algorithm. Did I show you? Have you heard about extended Euclid algorithm? Have you heard about this? Yes or no? Okay. Sometimes it's asked that what is the value of when you are dividing it with modulo 101. Then what would be this value? You know this value by Wilson's theorem. But what will be this value? Now you can understand that from here you can deduce like this. It could be written as 99 factorial into 100 congruent to, say, 100 modulo 101. Now since the everything is within Z101, right? Z101 star. Since this is an element of Z101 star, the multiplicative inverse of this exists. So if I multiply both sides with the multiplicative inverse of 100, multiplicative inverse from both sides, okay, that will be fine, no problem. So if you multiply both sides with 100 inverse and then 100, that should be congruent to 100 into 100 inverse modulo 100, 1. And that gives you the idea what is 99 inverse congruent to 1 modulo 101. Understood? Okay, let's check, cross check. Why not? We have the software, so why not we should cross check it. So factorial 99 divided by how much? Divided by 101. Okay, let's see. You get the value 1. But you can calculate it on your just by hand by using this kind of concept, inverse concept. But if after that it's fine. But if this question is asked, 1 year this question was also asked, modulo 101, then what will happen? So till now it's fine. 99 you can calculate it, well, no problem, but now it's 98. So what you need to do, 99 factorial, so from here you can write it 98 factorial into 99 is congruent to 1 modulo 101. Now the question is, what is this value? So you need to multiply both sides by 99 inverse, then 98 factorial into 99 inverse into 99 should be congruent to 99 inverse modulo 101. That implies 98 factorial is congruent to 99 inverse modulo 101. Now the question is, how can you calculate this value? Okay, and that's here this extended Euclid algorithm comes into play. So have you heard about extended? In my previous classes, did I show you how to calculate this extended Euclid algorithm? It's not very difficult. Did I show you in my previous classes? I don't remember. In my number theory classes, I have already shown you. But in your classes, did I? Anybody?
No, sir.
Okay. So let's see how to do that. It's again a very simple number theoretic problem. So suppose you know that if GCD of AB equal to 1 or say D, if D is the GCD of AB, then there exists UV belongs to Z such that D equal to AU plus BV. That you know, all know? This part you all know? This part? This part is known to all of you? This one, this result is known to you or not? Is this result known to you?
Yes, sir.
Very good. Now suppose I want to find the multiplicative inverse of A. Okay. So I want to find the multiplicative inverse of A in Zn. Suppose I want to find the multiplicative inverse of A in Zn. Zn star. Okay. So when the multiplicative inverse will exist? When GCD of A and N equal to 1. Now if GCD of A n equal to 1, then there must exist some U and V such that AU plus NV equal to 1. Now take mod both sides. So AU plus NV congruent to 1 modulo N. Okay. That implies what will be this value? What will be, since this is a multiple of N, so this value becomes 0 in modulo N. As a result, it will become AU is congruent to 1 modulo n. So that implies, who is the multiplicative inverse of A? Who is the multiplicative inverse of A? Tell me, who is the multiplicative inverse of A? U is the multiplicative inverse of A. So you are done basically. So you can find this. So the question is, how do I express this number? So what you need to do is GCD of 99 and 101 is 1. So GCD of 99 and 101 is equal to 1. That implies there exists UV such that 99 into U plus 101 into V equal to 1. That in turn imply 99 into U plus 101 into V is congruent to 1 modulo 101. That will imply 99 into U congruent to 1 modulo 101. So if you are able to find the value of U, then you are basically done. So the question is, how do I find the value of U? And that is known as extended Euclid algorithm. Okay. So first, what I am going to do is that you had two numbers, 101 and 99. Take the bigger one and write the bigger one in terms of the smaller one. So 1 into 99 plus 2, right? Then take the smaller one here, that means 99 equal to, use this as this. So this is 48 into 2 plus 1. Not 48, this is 49 into 2 plus 1, right? So now you are changing the role. Previously, you are dividing with 99 and you get the remainder. Now it was, you are dividing it with 99, now you put it here and then divide it with the remainder, that means 2. So you write it. So continue the steps till you get 1. Okay, till you get 1, because we started with the number which are relatively prime. Now do some back calculations. So 1 is written as, from this step I just make a side change here. So 99 minus 49 into 2. Okay, then put the value of 2 from here, that is 99 minus 49 into, what was the value of 2? It was 101 minus 1 into 99. And what do you get? So minus 49 into 101, and then this is plus 49 into 99, and this is plus 1 into 50 into 99. So now you can see that you represent 1 in terms of, this is your, say, U, and this is your V, right? So now if you make a modulo 99, what you will get? Modulo 101, then you will get, so this value will become 0 since it's a multiple of 101. This is 50 into 99 modulo 101. So 50 is the multiplicative inverse of 101, multiplicative inverse of 99 modulo 101. Okay, let's check with the software. So what is the multiplicative inverse of 99 modulo 101? And since I want to calculate inverse, so this, and you see that this is 50. And you can calculate this very easily by using your hands, just simple calculation. So 1 year it was asked, what is the remainder when this is divided by 101? Now you see that this is nothing but, it was how much? It was, so up to what we were here? We were here. So finding 99 inverse is sufficient for us, and 99 inverse was congruent to 50 modulo 101. So you can check now by using this factorial method. What is the factorial when you divide it by this? So 98 factorial is divided by 101. You can check by software. So 98 is divided by this. Let's check that. We get 50. Okay. So that's number theory. By using this congruence method, this symbol is very powerful. You can do many things by hand, which even the computer takes some time. You can easily do that. Okay. Is it clear to all of you? Now, if somebody wants to prove the Wilson's theorem, it's also not very difficult. It's also very easy. Just I'm giving you the hints. So what is Wilson's theorem? So that's the last one that today I want to do. It's very easy, not very difficult. So let me write it again. Wilson's theorem. What it says, if P is a prime, then P minus 1 factorial is congruent to minus 1 modulo P. Okay, proof. Okay, if P is 2, if P equal to 2, then 1 factorial is congruent to minus 1 modulo 2. Because in 2, modulo 2, minus 1 and plus 1 is same. So the result is true. So let P is greater than 2. So consider ZP star. Okay. Now in ZP star, what are the elements are there? If you look at, class 1 is there, class 2 is there, class 3 is there, class P minus 1 is there, class P minus 2 is there, and so on, right? Now let us try to find out which elements of ZP star are self-inverse. That means, for example, suppose I considered Z7 star, I want to find which element is self-inverse. That means, suppose A is that element, self-inverse means A is the multiplicative inverse of itself. That means this should be equal to 1. That is A square class equal to class 1. That is P divides A square minus 1 equal to A plus 1 into A minus 1. Since P is prime, that implies either P divides A plus 1 or P divides A minus 1. That is either P is congruent to, either A is congruent to minus 1 modulo P or A is congruent to 1 modulo P. So from here, what we see that within this ZP star group, only class 1 and minus 1 is same as P minus 1. So they are the only elements of ZP star which are self-inverse, and no one else. Okay. So if I write it in a bigger way, then the elements will look like this. Say class 1 into class 2 into class 3 into class 4 ... say class P minus 3, class P minus 2, class P minus 1. So all elements of ZP star, out of which the inverse of class 1 is class 1 itself, the inverse of class P minus 1 is the P minus 1 itself. But as all the remaining elements are the elements of ZP star, that means they are the elements of a group. So inverse of this will also exist, this will exist, this will exist, and all the inverse of these elements will exist, right? Now you see that there are even number of elements. since P is odd, so there exists even number of elements because we assume that P is greater than 2. So P must be odd. So here, how many elements are there? Even number of elements are there. Okay. Now you see that inverse of 2 exists, and that inverse of 2 must be sum of the elements from here, because it can, the inverse of 2 cannot be 1, or inverse of 2 cannot be P minus 1. So inverse of 2 must be some element, and it is not a self inverse because they are only self inverse here. So inverse of 2 must be one of the some elements from here. Similarly, inverse of 2 will somebody from here. So can anybody tell me what would be the product of this whole term? Product of this is how much? Product of this is how much? Quickly.
P minus 2 factor.
Okay, not bad. But from group theoretic viewpoint, this product of this term? 1. Very good. Because the inverse of this will be something within here. Say some k is the inverse of class 2. Inverse of class 3 will something is there. Say class I is the inverse of something. So if you multiply this with k, it becomes 1. Multiply 3 with I, this becomes 1. And there are even number of elements. And every element does have the multiplicative inverse. As a result, the product of whole thing will become 1. Okay, but if you look it quite carefully, as he has already given a kind of hints that if you make a product of all those things, the product value is how much? 1 into 2 into dot dot P minus 1. That means this is P minus 1 factorial. Okay, or just now we have seen that this value becomes 1. So it becomes P minus 1 only, same as P minus 1 factorial. And just now the way that we have seen that, that is same as P minus 1 factorial is congruent to P minus 1 modulo P. And P minus 1 modulo P is same as minus 1 modulo P. So we are done. So that's Wilson's theorem. Is it clear? So if somebody wants to study it with details, in my chapter 10, Basic Modern Algebra with Applications, you will find the whatever I told you in the whole class, everything is written with all the proper justification from group theoretic viewpoint. So now you will able to solve my problem set on number theory. There you will find also more interesting problems. And believe me, many of the problems are from many competitive exams, starting from JAM, TIFR, NBHM, NET, GATE, etc. So for you, JAM is more important, and many institutional exams like ISI exam or NBHM or TIFR exam. So for you, these problems are also very important. Okay, so any question? If you have, please let me know.